Okay, we're in section 12.3, and we're talking about the properties of logarithms. I went over those properties in the previous video, and I wanted to finish up that section here now. We're on problem 16. Write each expression as a single logarithm and assume that all variables represent positive real numbers. Okay, so part A, 3 times log base 5 of u plus 4 times log base 5 of v. What does that look like as a single logarithm? Well, law 3 was saying that powers can come in front of logarithms. I could also read this right to left. Like if I have a multiplier of r, I can pull that back inside of the logarithm so that it's a power of the inner part. Okay, and I'm going to do that to begin this problem here. I'm going to pull the 3 inside of that first logarithm, the 4 inside of that second logarithm, so that they are powers of the inner part there. Now I can use law 1, which is saying that if you're adding 2 logarithms with the same base, you can combine that to a single logarithm by multiplying the inner terms there. All right, so I'm looking at log base 5 of u cubed times v to the 4th. And that'd be my answer. There's my single logarithm. Part B. Okay, let's get a single logarithm out of that. Well, the first thing I'd want to do is take care of the 2/3 here. I can use law 3 and pull that inside of the logarithm so that it's a power of the inner part. Okay, and I'm going to have the ln of 8 to the 2/3. I'm leaving the second term as is for the moment. 8 to the 2/3. So I can very easily get that by using what I already know about converting an expression with rational exponents over to radical form. We learned all about that in section 9.2. 8 to the 2/3, that's the same as the cube root of 8 squared, and the cube root of 8 is 2. 2 squared is 4. So 8 to the 2/3, that's 4. With the other logarithm here, what you don't want to do, and some people might want to do this, is they might want to distribute the ln notation into these two terms. You can't do that. Okay. Instead, 3 to the 4th is 81, right? And 81 minus 8 is 73. So now I'm ready to get my single logarithm. I'm subtracting 2 logarithms, and I can use law 2 here. They got the same base. And I can combine those to a single logarithm now by dividing the inner terms. Okay, we're going to have the ln of 4 over 73. Then there's my single logarithm. Part C. Okay, let's get a single logarithm out of that. The first thing that I want to do is on the first and the third terms, I can pull those multipliers inside so that they're powers of the inner part there. Okay, 3 log base 6 of x, that's the same as log base 6 of x cubed. 1/2 log base 6 of x minus 7, that's the same as log base 6 of x minus 7 to the 1/2 power, or x minus 7 to the 1/2 power, that's the same as the square root of x minus 7 using radical notation. You can leave the second and fourth terms as is. Now, I would say let's just go right to the answer at this point. We got log base 6 on all 4 of these. With the first 3 terms, I'm adding, and so using law 1, when I go to get a single logarithm, I'm going to be multiplying the inner terms together. Okay, so I've got log base 6 of 4 times x cubed times the square root of x plus minus 7. And then the minus log base 6 of 5 means that I would divide by 5 using law 2 here. Okay, and there's my single logarithm then. In the last section, we were doing some things with finding values of logarithms, and in those problems that I had shown you in the last section, we were using the definition for all of them, actually, and that's an okay approach. But the fact that we've talked about our properties of logarithms now, we can use those to find values of logarithms as well. Okay, do not use a calculator. We don't need a calculator for any of these four. In part A, if I want to find log base 8 of 2 plus log base 8 of 4, well, I'm adding two logarithms that have the same base there, so I can use law 1 and get a single logarithm out of that by multiplying the inner terms. I'm going to have log base 8 of 2 times 4 is 8. And then I can use law 5, which says if the base and the input number are the same, you always get 1. Log base 8 of 8 is 1. Okay, so log base 8 of 2 plus log base 8 of 4, that's equal to 1. Part B, ln of e to the negative fourth power. Well, I know powers can come out of logarithms, right? So I'm going to have negative 4 times the ln of e. The ln of e is the same as log base e of e. And again, whenever the base and the input number are the same, you always get 1. So the ln of e, that is 1. Negative 4 times 1 is negative 4. I had mentioned in the previous video, I think, or maybe it was the one before that, the ln of e to a power is always going to be that power. Okay, so the ln of e to the negative fourth, that's negative 4. ln of e to the sixth, that's 6. Okay, etc. Part C, log base 3 of 3 to the 71st power. Well, 71 is a power that can come in front of the logarithm, and log base 3 of 3 is 1, right? Since the base and the input number are the same, you just get 1. 71 times 1 is 71. Okay, and of course another option that I could have used here is law 6. A is 3, right? X is 71. So you're just going to get 71 out of that. Law 6 is, to me, is really just the combination of laws 3 and 5. Okay, and then part D, log base 2 of 8. Well, 8 is the same as 2 cubed, and that's how I'd want to think about that, because now the problem becomes just like this one. 3 is a power, so that I can pull that in front of the logarithm. 3 times log base 2 of 2, log base 2 of 2 is 1. 3 times 1 is 3. So one strategy with working with logarithms and simplifying is, try to get the base and the input number base to be the same. Now you can't always do that, okay? Log base 2 of 8 was an easy enough calculation to work through because 2 cubed is 8. Now what if I wanted to find log base 2 of 9? Well, 9 is not a power of 2 like 8 is. Okay, so this problem becomes more difficult in trying to get the base to be base 2 inside the logarithm. Now, because it's a problem here, I would want to consider changing the base. Okay, I'm going to use the change of base formula and a calculator to evaluate each logarithm. We'll go nearest 3 decimal places with rounding. Now, when you change the base of a logarithm to a new base, it doesn't matter what the new base is. It's just, usually when we change the base, we want to make it either base e or base 10 so that we can then go to the calculator. Most calculators have a log button and an ln button. Okay, I don't have a log base 2 button. Okay, so in the current form, like, it's not just a go right to the calculator type deal. Okay, even the high-tech calculators, you can't enter in special bases. All right, so we'd want to change the base here. I'm going to be using the change of base formula, which is law 8, and I'm going to change the base to be base e. Now, when I'm working with base e, I'm working with the natural logarithm, right? So I'm going to have an ln in the numerator and an ln in the denominator. In the numerator, you're going to have 9 as the input, and in the denominator, you're going to have the ln of the old base. The old base is base 2. Okay, so log base 2 of 9, that is equal to the ln of 9 over the ln of 2. Now, the nice thing about using the change of base formula is because my calculator has an ln button on it. So now I can go to the calculator and type in ln 9 divided by ln 2, and I get 3.170 if I go nearest 3 decimal places. Okay. Now I mentioned that it doesn't matter what the new base is. So I've done the calculation again using base 10. If I'm changing the base from base 2 to base 10, the only adjustment is going to be, okay, instead of this being an ln, it's going to be log. Log base 2 of 9, that's the same as log of 9 over log of 2. All right, let me go ahead and type that into the calculator. Log of 9 divided by log of 2. I get the same thing. I get exactly the same number. So that's my point, is that it doesn't matter what the new base is. Okay, it's just, obviously you want to try to get base E or base 10 so that you can go to the calculator. Like if I were to change this base to base 5, it's like, why did I do that? I don't, so, something to keep in mind. But ultimately, it doesn't matter what the new base is. All right, let's take a look at part B. Log base 2 of 6 plus log base 7 of 19. Well, I can't easily rewrite 6 as 2 to a power, and I can't easily rewrite 19 as 7 to a power. So this would be another great example of a situation where I'd want to change the base. So let's change the base on both of these here to base E, and then we can go to the calculator. We're using the change of base formula. So the log base 2 of 6, that is equal to the ln of 6 over the ln of 2, plus log base 7 of 19, that is equal to the ln of 19 over the ln of 7. Okay, now I can go to the calculator and type in this first one here, the ln of 6 divided by the ln of 2 is roughly 2.585 if you go nearest 3 digits on that. And then plus ln of 19 divided by ln 7 is roughly 1.513 if you go nearest 3 digits. Of course, you can type in the whole thing all at once too if you want. You'll still get the same answer, which is 4.098, I guess, for this problem. Okay, now, of course, I can change the base anytime I want. I could use the change of base formula here. It's just there's no reason to do that. I can very easily get this answer without a calculator. All right, so something to keep in mind. The properties of logarithms and the definition of a logarithm are very important. Make sure that you know those. I've commented on the the fact that the definition is probably the most important thing to know when it comes to logarithms. But knowing our properties is also handy. All right, at this point we are now done with section 12.3. Be sure to look at the homework problems here on page 982, the odd numbered problems there.